Hi, I'm Homing. This is my second research paper for the course Engineering Self-Adaptive Systems. This paper is called Hybrid Monitoring Solutions based on Cloud Computing for Autonomic Middleware Level Scalability Management within IoT systems and different SLA traffic requirements, which is written by these three authors in 2020. This research paper intends to tackle the scalability issues in IoT networks, as offering high efficiency and intelligent decisions with a minimum human intervention. The IoT networks face challenges in terms of increasing consumers, including users and devices, as well as massive data transfer. These difficulties affect the performance of the IoT architecture. For example, it's challenging for the sensing layer to connect a huge number of devices together. Additionally, massive requests result in long waiting queues at the layer. Moreover, at the application layer, the availability of system functionalities becomes poor. However, as a new kind of internet, the IoT network has been rarely offered with effective solutions related to the scalability issues. In addition, with limited functional metrics and execution policies, few proposals can tackle heavy network traffic. For example, recent works use only one metric called round trip time (RTT) to evaluate whether the system should be scaled. Without considering RAM and CPU, these solutions limited system scalability. Moreover, field research take into account the standardization of systems architecture. In other words, most solutions provided by studies only work for specific issues. In this section, let's review some interesting approaches. First, a smart city network framework called Fog Computing Architecture Network provides approaches to improve energy provisioning and latency. However, without considering real-time metrics, this architecture is not compliant with SLA traffic requirements. Next, fog off everything. An energy efficient computing architecture is designed to offload the traffic between devices and remote clouds. However, this framework doesn't think about any standardization. Finally, several approaches utilize traffic oriented mechanism to drop invalid traffic in case of data and consumers overload. But these solutions don't consider the utilization of resource consumption, such as CPU and memory. In order to address the scalability issues mentioned above, as well as overcome all limitation of existing solutions, the authors in this paper propose a solution called IoTScal Hybrid that takes into consideration QoS metrics such as RAM, CPU, and RTT. Additionally, it enhances the compliance standardization for IoT. The architecture of this solution consists of three key components, namely scalability enhancement component, autonomic manager, and virtualized OM2M platform. As a monitoring component, the autonomic manager collects real-time information such as CPU usage, RAM, RTT, and success rate. Then the component sends policies to targeted components. The scalability enhancement filter requests, classify and distributes requests to achieve load balancing. After that, a controller will forward traffic to the OM to M or redirect to virtual OM to M. Compared to existing solutions, this paper proposes an architecture that handles more traffic requests in case of overload. Moreover, this framework is a hybrid architecture that combines resource-oriented and traffic-oriented mechanism, which improve resource consumption, such as RAM, CPU. Additionally, the architecture has more intelligent decisions and specific plans to execute. In addition, this architecture is applied with standardization. To evaluate the architecture, the authors simulate three situations where the M2M platform receives HTTP requests coming from different traffic sources, including industrial traffic, transportation, and non-IoT traffic. Moreover, different requests are sent alternatively at a certain interval to deteriorate the system state step by step, which is designed to simulate the threshold state of the system. Finally, the test results show that the architecture improved the scalability of the OM2M platform through satisfying more HTTP requests than existing proposals in case of overload. Additionally, the CPU usage and the RAM consumption are optimized. Finally, in terms of critique, this paper was well structured. However, the execution policies of this architecture are designed based on fixed system standard value. In addition, test scenarios are not completed enough to conduct a comprehensive evaluation of the performance of the architecture. Furthermore, the discussion about the limitation of the architecture was not comprehensive. Thank you.